The lista?
No, correção.
Correção. Of what? Oh, no. Maybe I'll bully Walnut to do it. Yeah. Okay. So let's go back today to random things. So remember the following theorem, that probability that GMP contains a triangle converges to 0 or 1 if P is much smaller than 1 over root n, P is much bigger than 1 over n. So an actual question is, what happens if P is a constant over n? Right. So we saw in the example of the random graph being connected that there was a very sharp threshold. Right? So you changed P by a factor of 1 plus or minus epsilon, they probably jumped from close to 0 to close to 1. So here we're going to see for the case of the triangle, and it's true more generally for any the existence of any particular small subgraph, that we do not get a sharp threshold. We're going to prove the existence of a coarse threshold. Okay, we're really actually going to determine exactly what happens. Okay. So what I want to show is that this is C, and this is the probability there's a triangle. Then as C goes from 0 to infinity, this probability is going to sort of go up something like this. Okay, so let's try and determine the shape of this curve. Okay, so any ideas?
That graph is the limit on n?
Yeah, so this is, I mean, that graph is not supposed to be too precise. This is just, yeah. There's an artist rendition of what's going on. So yeah, we'll try and prove some statement of this type. But yeah, it's a limit as n tends to infinity, exactly. Or just the curve for some very large n, whichever. So, the idea is for a bound in either direction. So here's a silly idea. Let's go through each of the triangles in the complete graph in turn. Just ask them one by one if they're a triangle in GMP. Okay, so let's list T1 up to Tn choose 3 be the triangles in the complete graph. Okay, so it's going to list them in some order. Right, there are n choose 3 of them. And let's just ask one by one if they're present. So let's let Bj be the event that Tj is contained in GMP. And we're interested in the probability that none of these bad events Bj happen. Right? The probability that there's no triangle. Right, so you're going along, you say the first triangle, are you there? No. Second one, no. Third one, no. Fourth one, no. As soon as you get a yes, you can stop. Right? You get a yes, then you can say, okay, so there is one. But it's, as long as you're getting no's, you want to know what the probability of the next no is. So what's the information you have so far? Well, you have a bunch of no's. And you want to know how much those no's affect your probability. Right? So we can write this as the product from j equals 1 to n choose 3. And I'll call this I of the probability of bi complement given b1 complement intersection bi minus 1 complement. Right? Saying given but you've only received no's so far, what's the probability of the next no? So what do you think about this probability? Roughly how large do you think this probability is? What's the probability? So what you've seen is it's a bunch of non-triangles. And now you want to say, now you're given a triangle, what's the probability that it's present? So if you didn't know anything, what would the probability be? P cubed. But you do know some stuff. You know that there haven't been any triangles so far. How much information is that? Is it a lot of information? Is it a little bit of information?
Depends on the amount of intersections.
Right, yes. So yeah, so you're looking at this particular triangle. Yeah, so you're answering in a slightly more advanced way. So this one we're looking at, there's a bunch of potential triangles hanging off here that we've seen none of them are present, and a bunch of here we've seen none of them are present, and none of these are present. We don't really know about this edge. I mean, we just know these triangles are not present. So thinking in a less precise way, how much information is it? So how many triangles should we have seen typically? Well, P is C over N. What's the expected number of triangles? We're using this notation is P cubed N choose 3, which is roughly what? Yeah, we know what P is, right? P times N is C. So it's roughly C cubed over 6. Right? It's a constant. So we should have seen C cubed over 6 triangles at the end. Okay, earlier even fewer. We should have seen a constant number of triangles, but we saw none. Should that really change your probability a lot? Probably not so much, right? Okay. So that's what we're going to prove. And right, so the precise statement will depend exactly on these intersections. So first, so this should be roughly 1 minus P cubed. Right? This is a question mark, I guess. Is this roughly 1 minus P cubed? So first, I claim that it is either at least or at most. You tell me which. Is this probability at least 1 minus P cubed or at most 1 minus P cubed? Right, so what's the argument?
Because there is no intersection
Uh-huh.
If there is intersection with some of the triangles,
Yeah.
then you lost some.
Right. The edges got a bit less likely. So the triangle became a bit less likely. So the complement became a bit more likely. So it's, yeah, at least this. Yeah. Yeah, okay. The logic was correct, so whatever the answer was. Yeah. Yeah. So that's actually got a name. It's called Harris's lemma. And it's often, by people in percolation, often called the FKG inequality. So Harris proved it in 1960, I think, and FK and G proved a generalization in the 70s, and people in percolation often use the generalization. But even then, even when they use Harris's lemma, they call it FKG. So the correct thing is Harris's lemma. So what does it say? So we're looking at two events. So what is a property of these events that we used in order to make this deduction? What was the argument? The argument was if there's not having this triangle cannot help you have this triangle. It gives you negative information. So why is that? It's because both this triangle and this triangle want edges, right? For them to be true, edges help. They're both increasing events in the set of edges. So it's A and B events increasing events. So what I mean by that, so I'm going to think of E and F as being subsets of 0, 1 to the n. So you could think of this n as being little n choose 2, and these 0, 1s encoding edges being present or not. And increasing means that if x is in E and x is at most y, then y is in E. Right, where these are vectors in 0, 1 to the n. And less than or equal to means less or equal in each coordinate. Does it make sense? So if you're thinking of properties of graphs, so you can think of these being families of graphs, and increasing means if you add edges, you stay in the property. So exactly the same thing as we had in the BOLLOBÁS-Thomason theorem. It's the same notion of increasing. Is it okay? Then the probability of E and F is what? What should it be? At least or at most what? What was the statement we used here? So perhaps I'll write it more in that form. Probably E given F. So if F occurs, meaning there's a triangle or meaning there's no triangle, whichever way around you're doing it, E and F are both in the same direction, they're both increasing in the same direction, that should help E to occur. So there should be at least the probability of E. What's another way of writing that? Let's multiply both sides by probability of F and replace this by intersection. Okay, so just the same thing. Is it okay? So, I hope it's obvious that if both events are decreasing, then the same inequality holds. just turn the world upside down. Swap 0 and 1. What if one is increasing and the other one is decreasing? Then you exchange the order, and it follows from this. So E is increasing, and F is decreasing. Then the probability of E and F is at most the probability of E times the probability of F. Okay, this is just an aside. To get this, what should you do? Just apply this to the complement of one of them. Right? What you'll see is probability of E and F complement, probability of E times 1 minus F. If you just play around with it, you'll see it gives exactly this. Okay, it's not difficult. Okay, so proof of this merely as an exercise. So just simple induction on it. Maybe we should do it. Who wants to do the proof? Maybe we should do the proof. So if we do the proof, then we might not have time for an application at the end. I quite want to get to the application. So I think I'm going to leave this as an exercise. Proof is an exercise. Proof exercise. Use induction. On n. Okay. Yeah.
So does that only hold for events that are in that space or in a space like that, or like, are you assuming that the space is 0, 1?
Thank you. I'm totally cheating. I want to put a little p here. So I want to choose. So, as I was stating this for like a uniform probability, but really we're going to apply it in more generality. So I want this pp to mean. Thank you for this is a very good comment. That we choose the probability of a certain x in 0, 1 to the n is p to the number of 1s in x times 1 minus p to the number of zeros. Right, so we choose each coordinate independently at random with probability p. Probability of p of being 1. So we take, in particular, this corresponds to GMP. Right? So if we take n to be little n choose 2, and these things to correspond to the edges of the complete graph, and this is exactly an event in GMP having, the probability of GMP having the event. Sorry, thank you. Uh-huh. I hadn't defined the probability measure. So, yeah, I don't mean that it holds for any probability measure. I just want to claim it for this probability measure. Yeah. So there are some probability measures which satisfy these kind of this property and some which don't. Thank you. So, is it okay? Right, so let's now deduce a lower bound, I think, on this probability. So the probability that there is not a triangle in GMP which equals the product from I equals 1 to n choose 3 of the probability of bi given so complement given b1 complement bi minus 1 complement is what? Is what? At least, thank you. Uh-huh. Yeah, to the power n choose 3. Right? And this is Harris. Right? Because each of these, all of these events are decreasing, so they're all positively correlated. So first I should even, let me say it, so at least from I to n choose 3 of the probability of bi complement. Right? This event helps that one. Right? So this is more likely than this. And this thing equals 1 minus p cubed to the n choose 3. Uh-huh.
Did you say decreasing?
I said decreasing. Yeah, they're all decreasing.
But with decreasing, we have the other.
No. So, yes. So thank you for the question. It's important. If they are both increasing, you get this. If they are both decreasing, you get this. If one is increasing, the other one's decreasing, then you get this. Right? If they're going in the same direction, then they help each other. If they're going in opposite directions, they hurt each other. Right? And this is decreasing, and this is decreasing. Right? Because it's not having a triangle. Right? So this helps this. Yeah. Thank you. Okay? Right. This thing converges to what? This is if P is C over N. Yeah, e to the minus c cubed over 6. Right? As n tends to infinity. Okay, so now I can say what this curve is. 1 minus e to the minus c cubed over 6. Okay, so let's prove that this is actually the correct answer. Okay. So to prove it, what do we need to show? We need to show that these events are sufficiently close to independent that this is a good approximation. Right? And an extremely useful tool for doing this is called Janssen's inequality. So let me state and then prove Janssen's inequality. So the setup is very similar to this, but let me maybe do it in slightly more generality. Okay, so I'm going to have set A1 up to AM, the subsets of n. So you should think of these as being just the triangles in the complete graph, but okay, they're just some subsets of 1 up to n. And let's once again have these Bj be the event that Aj is contained in, maybe I'll call it R, where R should correspond to GNP, so R is a random subset of 1 up to n. So probability that I is in R equals P for all I in N, all independently. Okay, so R is a P random subset of 1 up to capital N. And I want to know about this probability. Let me move it over here a little bit. So 87 or something. The probability intersection j equals 1 to m, none of these bad events occur, is at most something. So it's at least, so all of these are increasing events. So by Harris, this is at least the product Yeah, perhaps I'll say first what it's at least. So it's at least by Harris. So this is not the statement of Janssen, so don't write it down yet. I'm going to erase this in a second. It's at least the product of the probabilities of the BJ complement. So this is 1 minus probability of BJ. Okay, let's approximate this. If these probabilities are small, this is basically e to the minus the probability. So let's replace this by e to the minus this probability. And the product becomes a sum. So this is roughly at least this thing. What is this thing, though? This is just the expected number of bad events that occur. So x equals number of bad events. Right? So, just by applying Harris and doing some approximation, you can see this is at least e to the minus the expectation, which perhaps shouldn't be so surprising, because this is just the probability of a Poisson random variable being 0, where it has mean the expected value. Okay, so this is saying something like, sort of the worst case for this probability is when it's a Poisson random variable. Okay, so if they're independent of each other, then this is what you really get. So what to show is that if they're in some sense close to independent, then this random variable this x is somewhat close to being Poisson. Okay, but let me say these precisely. So it's at most. Okay, so in 2 cases, I need a little bit of notation. So let's write mu. So let's write x for the number of events bj that occur. Right? Let's write mu for the expectation of x. And let's write delta for something that's something like the variance of x. But let's write it explicitly as the sum over I tilde j of the probability of bi and bj. What does this mean? So this I tilde j means that ai intersect aj is non-empty. Okay? So we're taking the sum over all pairs that interact. If ai and aj are disjoint, then the events bi and bj are independent. So we're looking at all of the pairs of events that intersect. So the intersections come in exactly here. Just the sum of the probabilities that both occur. This looks a bit like the variance. Right? Okay. So what's the bound? Well, we might hope to prove e to the minus mu. Right? That's the best we could possibly hope for by Harris's lemma. The error is going to be plus delta over 2. Okay. This is going to be useful if delta is at most mu. If delta is bigger than 2 mu, then this tells you nothing. So if delta is bigger than mu, which it might be, we're going to prove a different bound. We're going to prove e to the minus mu squared over 2 delta. This is going to be only if delta is at least mu. Okay. Now these are the inequalities. Right? So it's saying that if delta is small, then you really get something close to the probability to the best possible. If delta is bigger, then okay, you get something a bit weaker, but still pretty good. This only gets really weak when delta gets to be mu squared, but that shouldn't be surprising, because when the variance is the expectation squared, then you really don't expect concentration. Right? So then really the probability should be of being 0 should be reasonable. Okay? So this is not very far from the truth. This is really what you can hope for. Yeah.
The probabilities of intersections of
Yeah.
atoms might be also relevant, right?
So this says that you don't need to worry about it. However, if you want a more precise probability than this, then yes, you have to take that into account. So this was done actually only fairly recently. So if you want a really precise boundless probability, then you can go to as many intersections as you like, and you get more and more precise results. You get for lower and lower order terms, basically. Yeah. Okay, so let's prove this, and then we'll give hopefully at least 2 applications today. Right. Okay. So I'm going to use Harris's lemma in the proof of this. Are you okay remembering it? It's okay? Okay. So just to warn you, you should remember this. And in particular, you should remember this. I'll use this for a moment. So this is not Janssen's proof I'm going to give. Janssen gave an analytic proof. This is a proof due to Bopanna and Spencer, which is entirely combinatorial and really sort of shockingly beautiful. So, and very surprising in at least a couple of places. So proof. This is of Bopanna and Spencer. Right, so let's just get set up. So we already basically did this. So I'm basically just going to do this again to reduce the problem to something else. So we're going to start out by proving the first one. Okay, so let's just observe again first the probability intersection of these BJs is just this product. The probability, complement, let's say it in fewer steps, 1 minus the probability of Bj given B1 complement intersection Bj minus 1 complement. Right? So just the same thing we did here. Just replace by 1 minus. Now, we're trying to go an upper bound. So now we can just use the fact that 1 minus x is at most e to the minus x. So this is at most e to the minus sum over j of this probability. Right? Just using 1 minus x is at most e to the minus x, and then pulling the product into a sum. Okay. So what we want is to show that this sum is at least mu minus delta over 2. And here's the claim which will imply that. So the probability of j given settlement is at least the probability of Bj minus what? Minus the sum over I tilde j with I less than j of the probability of Bi and Bj. Right. So just to point out, here I didn't make completely clear how many times I was counting the pair ij. I'm counting it twice if they're different. Okay. So I'm counting this as an ordered pair. So each one will be counted. Is that true? We're talking total nonsense. Yeah, because this is going to end up being delta over 2. Yeah. Sorry, and they're not equal. Yeah, and I is not equal to j, I think. Should I include I equal j? Looks like not. Okay, so if we can prove this, what does it imply? It implies that this sum is at least, so sum over j of probability bj is just mu. Right? So this first term just gives mu. And this error term, so we just sum this over j. So every pair ij gets counted once. But in delta, I said it were counted twice. So it's plus delta over 2. Right? I mean, whether you count it once or twice doesn't really matter. It just changes. I mean, we just agree on something. Okay, so if we can prove the claim, this is the claim. If we can prove the claim, then we've proved the first part. Okay? Nothing happened. It was just, I mean, this is all trivial, right? It's just saying this is enough. Okay? Right. So now comes the difficult part. Right. So let's give things some names. So let's let E be the event that's the intersection over all I less than j, let's say I tilde j, I less than j of bi. Let's let F be the intersection of I not tilde j, I less than j of bi. Okay, so just notation. So this thing is now probability of bj given E and F. Okay. We want a lower bound. So I think we're going to prove this by the time we get here. It's not just a few steps. But this first step is so surprising and weird that every time I teach this, I'm like, I must have got this wrong. So I've again forgotten what the step is.
Can you repeat why E intersection F is equal to concept?
Thank you. Yeah. Thank you. Yeah. Right. So in this first step, we're going to throw away basically something that's clearly way too much. Okay, this first step is going to be completely crazy. I'll try and get it right. Now, my claim is by Harris. So, I'll justify this here. My claim given BJ. So why is that? So E is the intersection of decreasing events, so it's decreasing. F is also decreasing. So E and F are decreasing. So if I erase this Bj, this would just be Harris. But that event Bj is there. So how do we deal with that? Well, what is the event Bj? Bj just tells you that these Aj is contained in your random set. So some of your coordinates are fixed. So the coordinates in Aj, they're 1. All of the others are chosen independently with probability p, with the same distribution. So it means that in the world where Bj occurs, you're in some lower dimensional space, but you're still just taking a p random set, and the event E given Bj is still a decreasing event in that world. Right? So you have some coordinates, you just fix some of them to be 1, but if you are decreasing in the whole world, you're also decreasing here. So E is still decreasing, F is still decreasing. So in that subworld, so this is Harris on n minus Aj. Right? Applied to the events when you fix all the elements of Aj to be 1. Right? So this is just Harris applied in this funny subworld where the event Bj occurs. So where every one in Aj is 1. I mean, not so funny. Very simple subworld. OK, but now we're almost done. So how do we deal with this thing? Well, I claim this is at least probability of Bj times 1 minus. So now I'm just going to use the union bound on these events. E complement means that one of these guys occur. That's at most the sum over I tilde j, I less than j, of the probability of Bi given Bj. This is just the union bound. Is it OK? So I've just bounded the probability that E fails to occur, as in at least one of these occurs, by the expected number that occur. So it's Markov. I'm just using Markov. But now we're done, because this is exactly this. Right? It's the probability of Bj minus, pull this inside, probability of Bi and Bj summed over the right thing. So I even had a little bit of space. Good. It's magic, no? Right. So it's harder to... So for this one, you give an F, E has to happen, and then B has to happen given E and F both happened. So this is actually equal to, this thing is equal to this times the probability of E given F. So we're throwing away the probability of E given F, which makes no sense at all. I don't even believe it's true. It's just completely insane. And there must be a mistake. It's so crazy. How can you possibly be allowed to throw away probability E given F? And I guess the point is that it's all kind of encoded in here, right? That you really are, so E, if F occurs, then E is also pretty likely to occur. So you haven't really lost that much. Yeah.
So then the first inequality holds. Sorry.
Yeah, we proved the first inequality.
But then that's for like no matter what delta.
Yeah,
is, right?
Absolutely, exactly.
But I don't see how the second bound's better than the first x. You're going to prove the second bound under
For delta large.
right?
So if suppose delta is 2 mu, then the first one gives you nothing. But the second one still gives you e to the mu over 4. Right? Yeah, so as soon as delta is bigger, the second one is much, much better. Yeah, so you're quite right. And this is an important observation. We didn't need this bound in order to prove this. And that's going to be important because to prove this one, we're going to use this one. Okay? So we proved this one for every mu and delta. Okay, is it okay? So this is the first magic bit of the proof is doing this insane thing. And then just applying Harris and the union bound and it works. Right? Just nothing happened, just magic. And you get this extremely strong bound, right? This is an amazingly strong bound. Saying that as long as things don't overlap too much, you have this incredible. This is already enough to solve this problem. Now, how do we prove the second part? All right, let's assume that delta is bigger. How are we going to prove a bound? So the problem with this argument is that these error terms become too big. They start to dominate the main term. So as we're adding in extra events, every event that we add in, it helps mu by adding the probability of this new bi, but it increases delta by more because there's so many other j's that intersect. What are they saying? They're saying there's too many events, there's too much intersection between them. So new events are not helping us. So what should we do? So in this weird situation when this argument, more events and not better. Of course, the more events you have, the smaller this probability is. Right? Adding more events here makes this smaller, but it's making our bound worse. Right? So observe that. Okay, so what you're supposed to say is, so let's not use all the events. Right? If we have too many events, let's not use all of them. We don't have to use all of them. Right? So we're going to use the fact that probability, the intersection of all of the bad events is at most the probability of the bad events in some set. For any set S we like. So let's choose a clever set S that has a really good mu but doesn't have a really bad delta. Okay, so we want to get lots of probability, the expectation as high as we can, but without having very much intersection between the events. How are you going to choose this very clever set? Yes, you could do that. You could try and pick them greedily one by one to avoid each other. How far are you going to get? I mean, at some point they're going to start having to overlap, probably. I mean, with triangles, you have like n choose 3 of them. So yeah, you could probably do that and then keep adding until it starts to hurt you, and then figure out exactly what point that is. Let's do something easier than that. How are we going to pick S? You want S to have these very clever, complicated properties. But I'm telling you, let's pick in a very simple way. Pick what, sorry?
Pick in just one.
Pick in juice. Oh, pick just one element.
Yeah.
Yeah, that's a very simple way of picking. It's not going to give a very strong bound. What's a good way that we know of choosing things in a very simple way that have very complicated properties that we couldn't possibly hope to find if we tried to construct them? Pick them randomly, exactly. Let's pick S randomly. Right. Okay, let's see. So let's put each element in S independently random probability Q, let's say. So probability that J is in S should be Q, and all independently. So when we apply the first part, which holds whatever mu and delta are, then we get, this is at most, e to the minus mu of S plus delta of S over 2, where mu of S is just what it has to be, sum over J in S, the probability, and delta S is the sum over I tilde J, I and J in S, probability BI intersect BJ. Right? So, what is mu of S? We don't know, it's something random. So we need to, so how are we going to pick this S? What are we going to do? No, I'll get rid of this. What we want is that there exists an S that has the property we want. We want there exists an S such that this is sufficiently small, or large, but it's positive, negative. Right? So we want an S where mu of S is big and delta of S is small. How are we going to show that such an S exists? Yeah, what should we calculate? Let's calculate the expected values. What's the expectation of mu of S? So each of these guys is present with probability Q. Right? So it's the sum over J in M, so J equals 1 to M, of the probability that J is in S times the probability of Bj, which is what you get if it's present. This is Q, so it's just Q times mu. Right? Now, what's the expected value of delta of S? Can you guess without me writing it? Sum of these things of I tilde j, probability that I and j are both in S, probability bi intersect bj. What's this? Q squared. It's q squared times delta. Here's the point. Mu is going down linearly in q, but delta is going down quadratically. So what we're doing is we're randomly sparsening our events so they don't intersect so much, because intersections go down quadratically in q. So what is the expected value of the thing we care about? What's the thing we care about? It's mu of s minus delta s over 2. Right? That's our exponent. It's okay? Equals q times mu minus q squared times delta over 2. So what should we choose q to be? Just to maximize this, let's say q equals mu over delta. Right? Equals mu squared over delta minus mu squared over 2 delta, mu squared over 2 delta. So there exists, the expectation of this is this. So there must exist an s for which this is really at least this. So it exists, this implies there exists s such that mu of s minus delta of s over 2 is at least mu squared over 2 delta. Right? This is what we want. Right? The expectation is this. So there exists an s which obtains at least the expectation. Right? Apply it for this s. This is at most e to the minus mu squared over 2 delta. Done. And there's one more thing we haven't checked. What have we not checked? So this condition had to be necessary, right? Otherwise, delta is very small, you get something much stronger. Where do we use this condition? Exactly, exactly. Q has to be a probability. It is, because it's the most one. So it's totally magic, right? Yeah. So you can use the probabilistic method inside a proof of an inequality about probabilities, which you then use to prove things about random graphs, which you then go back and use to prove things about deterministic things, right? I mean, okay, so we prove this. Oh, by the way, am I being mean to you by not giving you a 5-minute break in the middle? Would you? Who votes to have a 5-minute break? Nobody. Okay, so good. So carry on. I don't feel the need for one, but maybe, I don't know. What you guys do? Right, let's apply this. Let's apply this to prove that this is the right answer. Okay? This should now be easy. Okay. So, I'll raise the magic proof. No questions? It's okay? Yeah, so moral of the story, if you're trying to choose something, you don't know how to do it, seems complicated, the first thing you should try is try picking it randomly. Okay? Really makes your life easier. Right, so probability that there's a triangle, there's not a triangle in GMP, once again, recall it is the probability that none of these events occur where Bj is the event that Tj is contained in GMP, and these are the triangles. Okay. just to observe, this fits in exactly to our setup. Is it clear? So the AIs are exactly the triangles in the complete graph. Capital N is little n choose 2. These are the edges of the complete graph. So these are the edges of the complete graph. These are the triangles. M is little n choose 3. We're picking a p random subset of the edges. That's just GMP. Okay? So really it's exactly the right thing. So we just need to calculate mu and delta. So what is mu in this setting? Yeah, exactly. It's just p cubed n choose 3. Right? N choose 3 triangles, each present with probability p cubed. And what about delta? Let's just give an upper bound on delta. So we need to sum over pairs of triangles that intersect. Intersect means that their edges intersect, right? They're just sets of edges. So we need to deal with, so just actually things like that, right? Because if they're like that, then they're the same and they're not counted. So it's at most, how many of these things are there? At most n to the 4. Right. I mean, choose the vertices one by one. That tells you what the two triangles are. Times 5 edges, p to the 5. But this is a most mu. Right? Because it's about p squared. So it's roughly p squared times n times mu. And p is like 1 over n. So it's much smaller than mu. So it's actually much, much smaller than mu. So that means this thing is at most e to the minus 1 plus little o1 times mu, so times p cubed n choose 3. Right? Because the error, this is by Janssen. Because the error is delta, and delta is little o mu. OK, but then we're done, because this converges to e to the minus c cubed over 6 as n tends to infinity. It's actually a totally immediate consequence. So we've proved that this is actually, so this is the theorem. From problem to theorem. Theorem, this picture. Right? This is the limit of the probability is exactly 1 minus e to the minus c cubed over 6.
Sorry, I don't remember. Did we put some constraints on C, or is for all C?
For all c. For all fixed c as n tends to infinity. Yes, for any fixed c, the probability does not converge to 0 or to 1. It converges to this funny number in between, which is just e to the minus the expected number of triangles. Right? The probability of having no triangles is very close to e to the minus the expected number. It's very close to what it would be if the number of triangles were distributed like a Poisson random variable with the same mean, which, in fact, roughly speaking, it is. Right. So we didn't prove it, we just proved the probability of being 0, but really the number of triangles in, at least to some degree of accuracy, resembles a Poisson random variable. And it's basically just saying the triangles are almost independent. They're sufficiently close to being independent, at least at this scale, that everything's fine. Yeah. If, right. So if p squared n were not small, so if p is bigger than 1 over root n, things change. and then the triangles interact a lot. But at least when p is much smaller than 1 over root n, then they're more or less independent. Right. Okay. Let's, in the last 45 minutes, I'm not sure it'll take this long, we'll see. Let's try and give another application. So let's talk about, I'll put it over here. Yeah, so there are lots and lots of applications of this. Janssen quantities are a very kind of standard and extremely useful, extremely flexible tool. Most of the applications are perhaps a little more technical, so I'll give you an early application. So, in fact, I'm going to give you a result that wasn't originally proved by the Janssen quantities, but can be. So I'm going to talk about the chromatic number of a random graph. Okay. In particular, let's focus on the case where p is a half. So question, what is the chromatic number of g n a half? So does everyone remember the definition of chromatic number? Should I repeat it? Okay. So, what do you think? What bounds could you prove? Ah, okay. So have at least n over 2. So how would you prove that? Uh-huh.
And then one, something that at least one of them is going to have that number of neighbors.
Yeah, I mean, in fact, all of them will, with high probability. So,
And, well, if some vertex has an n over 2 neighbors, you need at least this many.
no. You don't, right? So, for example, this graph has chromatic number 2, right? Yeah. But so what have you proved? You haven't proved a lower bound of n over 2. You've proved an upper bound of roughly n over 2. N over 2 plus, let's say, little o n, right? Because all of the maximum degree will be roughly n over 2. And we already saw that just by a greedy algorithm, you can color with max degree plus 1 colors. OK, so that's n over 2, upper bound. Any improvements or any lower bounds? Yeah, that's a good idea. Can look for a clique. What's the largest clique you'll find in g and a half? So we can do the calculation, or you can remember that we already calculated it. When did we calculate the size of the largest clique in g and a half? In fact, I think it was on your test. Sorry? Ramsey number, yeah, exactly. It's the lower bound of the Ramsey number, right? You color randomly red and blue, that's the same as g and a half. And the largest monochromatic clique is the largest clique, and it had size, the inverse of 2 to the root, sorry, 2 to the k, root 2 to the k, right? So n is 2 to the k over 2 if k is the largest clique. So that means that k is like 2 log n. Okay, so it's at least 2 log to the base 2 of n-ish, because it's a clique. I mean, again, this is low. So let me just write approximately. Okay, so we've got it between log n and n over 2. Okay, it's better than nothing, but any improvements? Ah, okay. So let's try a random coloring. Seems not a crazy idea. Right, so we're going to randomly color with R colors. So what's the probability that an edge is monochromatic? So this is 1 over R. Whatever color this is, the other is the same. It's like 1 over R. So the expected number of monochromatic edges should be this times about n squared over 4. So maybe the probability of having no monochromatic edge is like e to the minus this, by this kind of idea. So the probability for a particular coloring. How many colorings do you have? R to the n. So the expected number of colorings with no monochromatic edge might be roughly this. So this is big if R is like n over log n or something. Maybe it's small, maybe it's better for it to be small. If R is smaller than n over log n. That's what I mean? I'm not really sure this is can you make this argument precise? To give a bound in either way? I mean, even if this is the expected number. Is that right? Because then this will be e to the minus n log n, and this will be like n to the n. So they're about the same order of magnitude. Yeah, I'm not sure that this is... I'm not sure if you can actually prove anything this way. But okay, it actually seems like a useful heuristic because it turns out that the answer is order n log n, n over log n, sorry. So So who can prove either bound? Who can prove a bound of n over log n in either direction? So one of the bounds is relatively easy. Or perhaps I'll even say very easy. Yeah, sorry, no, I'm being stupid. You're quite right. This is a proof of one directions, and actually it's going to give a better bound than the one I'm going to present, but it's slightly more complicated. So let's give an easier bound of a slightly weaker result than this argument gives. Yeah, the problem with this is, yeah, okay, so perhaps I won't say. Okay, so we need to recall a lower bound on the chromatic number that we've seen before. I think we've seen it before. I didn't tell you. I remember something I didn't tell you. I should put on your list. Sorry, I should give you a list as well. There are lots of things that I should put on your list. What's the lower bound on this? N divided by, yeah, exactly. Right. Why is this? Because what's a colouring? A colouring is a bunch of independent sets, right? Independent set 1, independent set 2, independent set chi of g. If all of these have size at most alpha, then n must be at most alpha of g times chi of g. Right? Okay, so this is just trivial. And how large is alpha of g, of GMP? GM1/2. Actually, let's just do at most, because that's what we proved. Yeah, 2 log n, right? That's exactly what we proved. We exactly proved, we're proving around the Ramsey number, it's at most 2 log n, right? So, correct number of GMP of g1/2 is at least n over 2 log to the base 2 of n, and I'm being careful with this because this is actually the right answer. So, theorem, maybe I'll do it over here. It's the theorem of BOLLOBÁS from the 80s. I forget exactly which year. That chromatic number of g1/2 is 1 plus 1 times n over 2 log to the base 2 of n with high probability. Okay, so this very simple argument gives the sharp. That is sharp. So at least up to this this leading order term, right? So there's a lot of mystery left in this little O1. So perhaps if I have time, I'll mention that briefly afterwards. Okay, so what we want to do, we want to show. So we know that this is sharp. We want to show that this is close to being sharp. So we want to cover the vertices very efficiently with these independent sets of size almost as big as they can be. Right? Okay, so how are we going to do that? Maybe so what do you want to do? So let's just try and do it greedily. Okay, let's just choose the first color class color class 1, let's just make sure it's big. Right? We need the average size to be roughly this. Just make sure this is this big. Okay. Now we need to find another color class. So let's just find another one. Here's color class 2. And continue. After some time, we found, I'm going to say, k color classes. And then there's some vertices left over. And what do we want to find in here? Well, we want to find a set that's independent, that has size at least 2 minus epsilon log to the base 2 of n. Right? So as long as we can do that, we can continue. OK, so let's continue as long as we can. And then there's some vertices left. What should we do with those? Well, as long as the number of vertices, yeah, please.
Can you repeat how are you taking subsets?
Right, so I haven't proved they exist, but I'm going to just try to choose one. If one exists, that's at least this big, I'm going to choose one. I'm going to arbitrarily. Yeah. So we just choose arbitrarily an independent set of this size, at least this size, while one exists. And then eventually get down to a set of vertices where you don't have any of these things. Now, if the number of vertices left over is much smaller than this, then we can just give each remaining vertex a different color, and we don't care. Right? So we want to show, here's the lemma. We want to show for every subset of the vertices of G1/2 of size at least, let's say n over log n squared. It doesn't really matter what we put here. There exists, so we'll say with high probability. So with high probability, G1/2 has the following property. Every subset that's sufficiently large contains an independent subset of size at least 2 minus epsilon log to the base 2 of n. So I claim the lemma implies the theorem via this strategy. Is it clear or is it not clear? So for how many people is it clear that the lemma implies the theorem? Nobody. OK, good. Thank you for your honesty. So what do we do? So we just do exactly what I said. So suppose that this property holds. Okay, so suppose that G1/2 satisfies this property, the one I stated here. Then what do we do? I claim we can just pick the guys of color to be color 1 to be any set of size at least 2 minus epsilon log to the base 2 of n. Then in what's left is a set S that's bigger than this. So we can pick another one. Let's continue. Continue until what's left has size at most n over log n squared. Right? So we can just greedily find color classes until we have fewer than this many vertices, because we just keep applying this property. Right, for every set S that's larger than this, there exists an I, so that's the next one. Right? Which is the right size. Is it not okay? Yeah? No? Maybe? Not sure.
So what you're doing is at each step you're coloring S. You're going to color S some color, and inside S there's an independent set.
So no, there's no. So the colors are these guys. So suppose after a certain number of steps, some earlier point, t. So I've gone t steps. So I've already assigned these vertices are color 1, these are color 2, these are color t. I've used my first t colors. And I'm left with a set that I'm calling S. And I now want to choose a set that I'm going to assign color t plus 1. And that set has to be independent, right? Because it's a proper coloring. Right? So what can I do? I apply this property. For every S that's big, so I'm assuming S is still big, I can find an independent set that's large. So here there exists an independent set. G1/2 has this property. There exists this independent set. I'm just going to take this, give these color t plus 1. And then remove them from S. And continue. Right? And I just continue until the set S, or what's left, has size at most n over log n squared. So I can't apply this lemma anymore. But now I can just give each of these a different color. Right? So how many colors have I used? I've used at most n divided by 2 minus epsilon log to the base 2 of n plus n over log n squared. Right? Do this for every epsilon. It gives the answer. Yeah?
Why do we have extra term?
This is to coloring these vertices.
But this should account for one color.
No. This could be, I mean, we don't know anything about what happens here. We have to give a different color to each vertex.
Okay.
Yeah. There is something that's the stupidest possible thing here. But it's small enough that it doesn't matter. Okay? Okay, so we need to prove the lemma. How are we going to prove the lemma?
So this implies the lower bound, right? I mean the upper bound.
Yeah.
Okay.
Yeah, the lower bound was this easy argument.
Okay.
Yeah, so this is the hard part, the upper bound. Okay, so you want to show that with high probability, every set S has this property. So what should we do?
Calculate the probability that there is that there exists as an S.
Yeah, so how are we going to calculate that probability? Sorry? Right, but so this event is kind of complicated. It's more complicated than this thing. It's not in that setting. Right, it's for every set S. So each S you would like to be a bad event or something. But then the bad event is just that there exists an independent set of a certain type, and it's not of this form. Right. So we need to do a simple step first to get us in this setting. It's just what we always do. If we want to show that every set has a certain property, so we're going to show there are no bad sets, so let's count the bad sets. So let x equal the number of sets S which fail the property. So S is at least equal to n over log n squared, and there does not exist a good I. We'd like to show that the expected size of x is small. So we want to know the probability that a particular S is bad. So here's the previous lemma. The probability, so let S be a set of size n over log n squared. Probability that there does not exist I in S, size of I at least 2 minus epsilon log to the base 2 of n, I independent, is at most something. Right. What do we have to beat? We have to beat the number of choices for the set S. So in particular, if we can prove, say, 2 to the minus n, then we're probably in good shape. Right. Let's try and show the probability that the set is bad is really small. Okay. Now, how are we going to prove this lemma? Now let's use Janssen. Right? Now we're in the right setting. Right? So what are our sets A? They're the I's, right? Exactly. A1 up to AM. So subsets of S, size of AI is 2 minus epsilon log to the base 2 of n. Right, and what is R? So we want I to be independent. So these are really, they're not subsets of S, talking nonsense. They're cliques in the complete graph on S. Right? So they're really, these A's are, right, so what's N? N is size of S, choose 2. M is size of S, choose this thing, which I'll call K. Okay. And the AI is the set of edges on a set I of this size, of size K. Is it clear? So the AI are the edge sets of these cliques. And what's R? So you want this set to be independent, so you want to have no edges of g1/2. So R is, it's the complement of g1/2. Right? R is the set of non-edges inside S. Yeah, very restricted S, if you like. Which is fine, it's still a half random set. Okay, so Janssen implies the probability.
Sorry, what is R?
Sorry? R is the random set here.
Yes, but I don't know.
Oh, sorry, it's the non-edges. It's the non-edge, the pairs inside S that are not edges of g1/2. So AI is contained in R means exactly that this is an independent set of size k. Right? And the probability that we care about is exactly this intersection of all of these bad events. Complement of these bad events. Right? But none of these things are independent. And how large is this? Okay, we still have time. Calculate an expectation. So mu is what? Mu is the expected number of independent sets of this size. Right? So it is S choose k, with m events. Each of them occurs with probability 2 to the minus k choose 2. Right? It's okay or not? So mu is the expected number of these events that occur. Each of them occurs, each of them is the edge set of a kk. So k choose 2 edges. And each is present, or not present, probably a half. So the probability is 2 to the minus k choose 2. How many are there? S choose k. It's the same calculation as we did with Ramsey, right? It's exactly the same thing. What's this? So I want this to be at least something. This is at least. So S is n over log n squared. So it's at least sort of S over k, 2 to the minus k minus 1 over 2 to the k. Right? Just using S choose k is at least S over k to the k. Right. This is a plus, so I can get rid of this minus 1. That just helps us. Now, S is n over log n squared, and k is about log n. This is at least n over log n cubed. We just ignore constants for now, they won't matter. 2 to the minus k over 2. K is 2 minus epsilon times log n. Right? 2 to the minus 2 minus epsilon over 2 log to the base 2 of n. But what's 2 to the minus log to the base 2 of n? So 2 to the log to the base 2 of n is n. Let's pull this down, n to the minus this. 2 minus epsilon over 2 is 1 minus epsilon over 2. So minus 1 plus epsilon over 2. But n to the minus 1 times n, they cancel. And we now have n to the epsilon over 2 over log n cubed. I'll put to the 4, whatever, to make sure it's smaller. To the k. Just to make it smaller. just because I was ignoring constants. So I'll put it 3 if you're happier. I mean, but I mean this thing wins, right? So it doesn't matter. Yeah. So just to show that I don't care, I'll put a 4. Whichever. You put a 10 to the 10 if you like. Okay. So this is at least n to the epsilon k over 3, because this is much smaller than that. And k is, what am I talking about? Ah, yes. K is like log n. It's at least n to the epsilon log to the base 2 of n over 2 or something. Okay? So mu is like n to the log n. Okay. What's delta? Maybe I'll do delta here. Can I erase this? Okay, delta is at most, so mu is at least this. I'll put it here. So mu is at least n to the epsilon, just say all about epsilon log n. It's not going to matter too much. Delta is at most, what? You're looking at pairs of independent sets that intersect. You know the probability of both of them. So this is size k, this is size k, this is size L. Let's say L is at least 2. So what do we have? S choose k. Maybe I'll just write it as, no, maybe I won't. So perhaps I can convince you that the only case you have to check are L equals 2 and L equals k minus 1. Right? Because everything else by convexity or whatever is worse. So once you're intersected a bit, so it's really painful to intersect a bit because you have to intersect in 2 vertices, you gain 1 edge, it's nothing. But every extra vertex is also painful, but then you gain more edges. And the last vertex you add gains you the most edges, and you don't have to count them twice. So the only ones you have to worry about, L equals 2 or k minus 1. So you can check. So yeah, just to not make things more complicated than they need to be. Right. So this is what? S minus k choose k minus 2, and then k choose 2, and then 2 to the minus twice k choose 2 plus 1. That's the L equal 2 case, which is basically, okay, so what's this roughly? So I want to say this is roughly S choose k squared, except we get sort of, there's an S squared over k squared here and a k squared. So it's something like k to the 4 over S squared, which is also roughly the probability that these things intersect in that much, times this thing. So it's okay. So this whole thing is roughly S choose k squared, 2 to the minus 2 k choose 2, times k to the 4 over S squared. Okay, so just some simple approximation gives you this. Because k is like log n, and this is like n. Right, this is like a polylog n over n squared times this thing, which is mu squared. Right? Sorry, you're all staring at me as I'm totally insane. But what I'm doing is actually it's just some totally trivial calculation. And I'm just saying if you don't see exactly how it works now, you can very easily check it for yourselves. Right? I'm just saying very quickly something utterly trivial. Okay? Yeah, please.
I agree with you that we only need to check the case where L
Yeah.
equal 2 and k minus 1. But when we bound the other terms,
Mm-hmm.
we will have like k terms, right?
Yeah.
And then
This is another log n. So the point, this is just log n to the 4. s is n over log n squared. So n squared times log n to the 8. And if you put a log n to the 10 to the 100 here, I don't mind.
So we are not getting.
Yeah, exactly. So we're going to win by plenty. Yeah, that's the point. Okay, so this is at most. So this first term is mu squared times log n to some large constant over n squared. Right? And then the second term is when they're almost the same. So you pick one of them, s choose k. You pick one guy not to be in and one new guy to be in. So it's times k times s. And then what is it? It's 2 to the minus k choose 2 for these guys. And then this one has to be a non-neighbor to these k minus 1. And this thing is mu times what? K times s over 2 to the k, basically. Mu times k times s over 2 to the k. What's s? It's about n. K is like log n. What's 2 to the k? 2 to the k is 2 minus epsilon log to the base 2 of n. So this is like n to the 2 minus epsilon. So this is like 1 over n to the 1 minus epsilon. Right? So this guy is much smaller than mu. And this guy is much smaller than mu squared. Right? And as a consequence, one of these bounds is good. Right? So if this one is also much smaller than mu, then we e to the minus mu. So it's either e to the minus, so let's say mu over 2, if this one is much smaller, or if it's much bigger, then this one also dominates this one, and we get mu squared over delta is like n squared over log n to the c. E to the minus n squared over log n to the c. But this one is mu is n to the log n. So is this one. Right, because this one is, this is crazy better. So what we're getting is not 2 to the minus n, it's almost like 2 to the minus n squared. We won by miles. So that's why I didn't want to do this too carefully, because you just win by so much. Let's not get bogged down in silly details. Okay? So do this calculation in any stupid way you like. You're going to get a bound that's good enough to beat this. Right? Even by miles. Okay, and that's the proof. Okay? Please.
Now to prove the previous lemma,
Yeah.
that should do an upper bound.
You just take a union bound over s. So just sum over all s. There's only 2 to the n of them. So the probability of failure here is almost 2 to the n times this. So still tiny. Yeah. So your probability of failure is super, super tiny. Yeah, so this is one of the first. So BOLLOBÁS didn't use exactly this method. He used martingales instead of Janssen. But it was one of the first applications of this idea that if you want to prove something about a random graph, use this sort of very strong bounds on probability, so these very strong tail estimates, to show that even if you sum over all subsets, still this terrible thing won't happen with high probability. And if this terrible thing doesn't happen, then you can just do something deterministic and greedy and simple. Okay, and this basic idea is one of the first and simplest applications of this very powerful idea. This is used now in all kinds of places. It's a very powerful and useful idea. Okay, so don't worry if you didn't follow all of the details of the calculation. As usual, no calculations like this will come up on the exam. I hope you noticed that all of the solutions to the exam should have been like 3 lines long or something. I was really like, if you wrote more than a page anything, then you were doing the wrong thing. Right? So calculations, don't worry too much about them. They're not difficult. It's just like some trivial work. It's the idea that I want you to take out of it. The idea that to prove this thing, to find this coloring, you show that with very high probability, GMP has this fairly simple property, and then you just pick greedily. Right. OK, so see you on Friday. Yeah.
This was for a lower bound? Or
This was for the upper bound. The lower bound was just this prime number of G is at least n over alpha of G. So on Monday, class will again be the mini course of Julian. But on Friday we'll have a. I'm not sure we'll do on Friday. We'll see. Anyway. But yeah, normal class on Friday. And hopefully Elista. Apologies.